Started the recording. So what are we talking about today? We started last time, actually, 2 weeks ago, because last week we had the break. We started last time to talk about history of Earth's climate. It's a fascinating subject. And let me take the slides, which I am using today. So if you go to my website under our lecture notes, you see history of Earth's climate is this link here. Let me just share the screen with the people who are connected online. Okay, so here we are. So again, on our lecture notes, you see here history of Earth's climate. If you click there, you get to Virtuale. Why? Because the slides that I am using today were prepared by a distinguished colleague, Professor Rossi, and they cannot be shared on the public domain because there are some pictures who are protected by copyright. So we can share them on the internal Virtuale reference website for lecture notes, but not in the public domain. So we need to get into Virtuale. Let me just get it and take the slides. I am doing this process step by step, so you know that indeed you have to log in into Virtuale and you know for the future how to get them. So history of Earth's climate, you see two links, papers. I don't think you need them. But of course, the link is there if you're interested in getting more information. That's it. And then if we click on history of Earth's climate, we get to our slides. Let me see. I think it's better if I download them because I want to use the slide in presentation mode. So let me just download it and then I'm sorry. Okay, sorry. Okay. 1 second, download. Here we are. And let's open it. Adobe Acrobat, very good. Okay. And 1 second. Just give me 1 second only. Okay. Okay. I think it is blocked. Just okay, here we are. Sorry, because I'm not using. Do you remember what is the key? Or let me see. For getting in presentation mode from Acrobat Reader, because I'm not using it, and just 1 second. Okay, no problem at all. Let's use it in this way for now. Give me 1 second, please. Okay. Anyway, let's use it in this way, which is fine. Let's see. I think I need to make access. Okay, we can use it in this way. Good. So let's, on the screen it's visible. Let me see if I can turn off some light. Okay, perfect. This is
Sorry, feel free loud, please. Down G5, right? Now you go over the.
okay, or maybe
This one.
this one.
Full screen off.
This is full screen. It's also presentation. Let me see. Ah, yeah. Good. Thank you very much. And let me see.
Yeah.
Okay, perfect. Thank you. Because I'm not using Adobe Acrobat because it's not open. You know that I am a fan of or a fanatic of open software. So this is a Windows PC. I cannot use my preferred visualization and software. Okay, perfect. So today we are talking about history of the Earth's climate and what is the reason why we want to talk about it. Because in order to understand current climate change, it is essential that we try to compare what we are experiencing today, what situations that were experienced by the Earth's environment in the past. And therefore, looking at past changes helps us to better understand what's happening today and to give an attribution to what's happening today. And give an attribution means identifying the drivers, the causes, attributing current climate change means getting support for finding solutions to mitigate it, and solutions to better understand what's going on into the future, so to improve our capability to predict what will happen during the 21st century. And basically, what is the principle leading us? The principle is taken by the so-called uniformitarianisms, which means that the laws of physics that we know apply today also apply into the past. And therefore, if we look at the outcome in the past from the laws governing these processes, we can better understand what's going on today. Okay, this is just a premise, a philosophical premise. What is important is indeed to emphasize what is our purpose. Okay, understanding what happened into the past. But it is a bit of a problem. Why? Because we don't have measurements, or we have only limited measurements. And let me just look at this graph. These are some graphs which already discussed about sea level change or temperature, evolution of temperature. But if you look at the start time of these graphs, which are taken through measurements, these graphs are depicted after measurements. You see the start time here is for sea level 1900. For temperature is 1850, which by convention is taken as the start date of the so-called instrumental period. We don't have regular measurements of climatic variables before 1850. We have sporadic measurements. I mentioned already the daily rainfall series in Padua, which started in 1725, and it's a relevant exception. It's the oldest daily rainfall series, daily rainfall record that in the world that we have available today. We have some marks, flood marks taken by the Egyptians along the Nile River. But actually, if we look in terms of measurements, regular measurements, then the instrumental period is located at 1850. And of course, this is too short. In order to understand climate variability, if we talk about glaciation, you may remember the last glaciation ended, or at least started to decline 11,000 years ago. So 200 years, less than 200 years actually, is nothing against 11,000 years ago. To better understand what happened 11,000 years ago, this is too short if we have only 200 years, not to speak about the whole of Earth's history. And take into account that some changes in climate are very slow. They take thousands of years to take place. And therefore, we have to look at something different with respect to data. We have to look, for instance, at the stratigraphy of some locations which are particularly suited for providing information on the past climate. If we look at the evolution of geology, we can go back in time. Actually, if you think of geological chronologies, if you think of eras, epochs, they are delimited, they are identified by looking at geological signatures. Geological signatures which can be derived in many different ways. And the purpose of today's lecture is to better understand, first, how to derive these signatures, how we can reconstruct the past climate, what is the information that we need, and second, of course, to compare what happened in the past with what we are experiencing today. And keep into account that what we are experiencing today is something that started, we suppose, after the Industrial Revolution. So it's something that is occurring since yesterday, because in geological chronologies, as I said, 200 years is like one day for our life. So it's really very limited. So we have to compare also the pace with which these changes occurred in the past with the paces that we are experiencing today. And when we talk about global warming, actually is the last 30 years, beginning of the 90s. So it's about 35 years since we started to observe some traces of global warming. It is indeed interesting to understand how this reconstruction of past climates are derived. Besides the information, which is very useful, it is interesting to know how these changes were derived. I already mentioned, for instance, tree rings, but tree rings actually go back in the past for a limited time. The history of Earth is about 5 billions of years long, and therefore, you know, we have to go back into the past much longer than the lifetime of a tree. So there are actually a lot of proxies, informations that we can use to reconstruct past climatic variables. And it's interesting to learn more about this information. I also want to spend some few additional words why it is important to compare what's happening today with what we believe it happening to the past. Because you may say, actually, it's not really important, because if we suppose that today, what's occurring today is due to human influence, you may say, was not there in the past. So what is the purpose, actually, of comparing things that may have caused by very different drivers? The purpose is that today, actually, we recognize that climate is a complex system, it's subjected to variability, which is also caused by natural behaviors. And it is extremely important when we experience a problem to identify the causes of the problem, because if we are in a way concerned by a problem, the first imperative is to better know it. It is dangerous what we don't know. Why it is dangerous what we don't know? Because when we are subjected to an hazard, if we don't know it, we are taken by surprise when the hazard materializes in a disaster. And the surprise has been recognized as the main problem, the main cause of damage. So we have to avoid surprise. To avoid surprise, we have to better know a problem, to better know the risk. And better know a risk means identifying the causes. And therefore, human influence, we believe it's one of the causes. But if there might be other possible drivers like natural variability, it is imperative that we can attribute what's going on to human influence on the one hand, natural variability on the other end. Other possible causes which may go beyond the natural variability, for instance, volcanic eruptions have caused, we know, several changes into the past. So for this reason, it is extremely important that we try to understand the past climate, beyond which we know just qualitatively, like, okay, we had glaciation, but we have to try to better understand the duration of this glaciation, what caused these glaciations, because still we have several open questions related to past climatic variability. So this is a graph showing the history, or let's say the subdivision of the history of Earth into periods, into what are called eras. Eras are mega periods, and the eras are those that you see listed here, the Archean, the Proterozoic. These are very old. You see that the formation of Earth goes back to about 4.6 billion years ago. These numbers, this order of magnitude, are extremely important. You have to remember them, because you can't talk about climate if you have not an idea of how long ago Earth formed. And if you make an experiment, you ask your friends or people in the street, how old is Earth? You will find that a few people only will get the right answer. And I have to say that when I was a student, I had no idea. And or also the date of what we believe was the origin of the human species. It's extremely important that we have an idea of these times, okay? So, in order to have an idea of these times, the classification of the history of Earth in mega periods, like the eras, is important. We are currently in the Cenozoic era. And once again, these subdivisions are identified based on geological marks and indications of which can be found in geologic records of changes that occurred over the Earth system. And we will see what are the changes that we believe, but you can see a schematization here, okay? And for instance, the location of a gigantic extinction here, which marks the subdivision between the Paleozoic and the Mesozoic. And you see the periods, the epochs, which are subdivisions of the eras, which are listed here, okay? And we are currently in the Holocene. The Holocene dates back to 10,000 years ago. So the era the epoch, where we are living now is the Holocene, and started about 10,000 years ago. And how it was identified, it was the start of the recession of the ice after of the glaciers after the last glaciation. The last glaciation currently is still ongoing, because as I will show later, we are in a cold period of the history of Earth now. So again, we are in a glacial period, we are in a glaciation in these days, but these glaciations started to retreat, to recede back about 10,000 years ago, 11,000 years ago. And the start of the retreat of the glaciers marks the subdivision between the Pleistocene and the Holocene. And we already discussed the proposal that has been made to mark during these years the start of a new period, of a new epoch, the Anthropocene. And the debate is, first of all, whether this is marked by geological records, because the approach that has been taken here to make this classification once again is based on geological records, like fossils, like stratigraphy, like limnology, like other markers that we will discuss later on today. So, according to this approach, to start a new epoch, we would need to identify geological marks of the human influence over the Earth system. And another discussion, another argument that is debated in this discussion is the duration, because if you compare the duration of the Holocene, 10,000 years, 11,000 years, with the duration of the other of the other epochs, you see that they are much longer. So there is this debate, which is just a curiosity, like, are we in the Holocene or the Anthropocene? Of course, these classifications are subjective, and it is not really important for our target, which is gaining a better understanding of what's going on in the current climate. Okay, but I like this picture, and which proves that on the right you have the instrumental periods, and on the left you have the whole history of Earth, and you understand that this is just a drop in the ocean, and we need to extend back to this duration, and it is not easy. And people started already a couple of 100 years ago to go back in the past. And of course, we cannot back into the past for 2.5 or 4.6 from the start of the Earth, billions of years. We cannot go back so far. But of course, with increasing technology, with increasing knowledge, and with artificial intelligence, we can extend back one step over the other. And today I will propose you a kind of a journey in the past history of climate. And you will see that this journey has been moved forward with subsequent steps. Like when you explore a cave, you go in the deep earth for steps. And then step by step, with improving technology, we can get deeper. Okay, this that you see here is a very recent reconstruction of temperature over Earth, and goes back, it's the longest so far. It's presented at the Smithsonian Museum in Washington, D.C. Actually, it must be very interesting to visit this museum, and if you get a chance to be there. And the only thing is that you have to book months in advance, so it is something that needs to be very planned with a long anticipation. And I tell you this because by chance I was in Washington before Christmas, and I said, okay, I have half a day free, let's go to the Smithsonian, and I didn't know that you have to book months in advance, so I didn't get there. Okay, so this reconstruction dates back 500 millions of years. It's the longest, so 500 million. History of Earth is, we said, 4.6 billion years long. The longest that we can go into the past for temperature is 500. Temperature is easier than other variables like rainfall, because we already discussed that it's slowly varying, is not so heterogeneous, and it can be inferred, it can be detected by means of several markers, several different markers. And we will explore today what are these markers, this information of temperature. But before I move forward, let's look at the global picture, okay, here. And what you see here is that we can distinguish today's temperature is about here, okay, this is today. We can distinguish between two zones of this graph, the blue one, which means iced world, which means that it's the blue one marks the periods where the Earth had the polar caps. Okay, and you see that actually it's not the longest part of the history of Earth. With the yellow-orange line, we mark the so-called greenhouse period, which means without polar caps, okay? So, and you see that here in this figure, several key points are marked. Let's try to explore some more of these key points, okay? So, greenhouse, icehouse, okay, the two different periods. Once again, the difference is polar caps or not, world with polar caps, world without polar caps. And first, what we observe is that variability is the normality. It is something that we know already. again, variability is the normality. What is the difference between variability and change? Okay, it is a semantic difference, but let's say that variability, we indicate with variability something that goes up and down. With change, we mark with the term change, something that is irreversible, that is going to change and change forever. This is a bit semantic because, of course, change may be part of variability. So variability means change, actually. If you look, for instance, at any part, any portion of this line, you see that there is change. If you zoom in, okay, if you just look at a small piece of this graph, you see each piece is change. And this change endures for millions of years. But then eventually turned into a down, into a decrease. Like here, number 3, you see a raise of temperature in the orange line, lasted millions of years, then reached the cap, and then went down. So variability change, it's not easy to distinguish them. In order to distinguish them, you need a very long record. Okay, like here, you see that overall it's stable, it's variability. Okay. I would say that 500 millions of years is a good period. It's only like 10% of the history of Earth, but 10% is not bad. I mean, if you compare 500 millions of years with 200 years, the data that we have available, you understand this is a good piece. So variability is a normality, but actually we also see that for very long time scales that could provoke an extinction, we had observed changes. So, I mean, the fact that after our extinction, maybe that the temperature goes down is something that is not reassuring, it's something that is still concerning. So it's clear that we have to better understand what are the causes of these changes in order to be able to make prediction. And I talked about extinctions because indeed these markers 1, 2, 3, 4, 5 indeed mark significant changes in the habitat, significant changes in the species that populated the Earth. Because indeed changes in temperature imply changes in ecosystems, imply changes in living organisms. So with the term of wine, we identify a diversification of marine life, a Cambrian explosion during a very high temperature period. Usually, when you get an increase of temperature accelerates the ecosystems, accelerates the dynamics of the ecosystems, and therefore favors an evolution of life. But of course, evolution of the whole ecosystem, diversification of living species may also mean that some part of these living species, some selected species may go to extinction. So number 2, polar ice cap formed and persisted for a long time. And then when the warm period came again, we had a radiation of reptiles. What means radiation? It means diversification of the species. It means that there was a diffusion and therefore an evolution of the living organisms that led to a diversification. Because when a living ecosystem gets perturbed, the ecosystem tries to adapt, but this adaptation may imply a diversification of the species. So we have several remains that testifies, for instance, that the dinosaurs, they extinguished because their organisms that was suited to the previous environment after a climate change, it was not no more suited for the new environment, and therefore they went to extinction, and their extinction favored, of course, the growth of new species, the diffusion, the radiation of new species, which took their place. With indeed number 3, you see the radiation of reptiles, and number 4, the radiation of mammals, which gave rise to a diversification of the species, and we get the big mammals that are still living today. They originated during this warm period. And then we had the last glaciation, the Pleistocene glaciation, which lasted up to about, as I said, 11,000, 10,000 years ago. And then there was an increase of temperature during the Holocene. However, as we will see, during the Holocene, the temperature was quite stable. And this favored the civilization, favored stable conditions, which allowed humans to settle down in very stable settings, stable on the long period. Okay, of course, if you look at the short period, you have perturbations like the Great Acceleration, marked with number 5. And the Great Acceleration is what we are experiencing today. And we have to locate this Great Acceleration into the changes, the dynamics of the past changes. Just to be clear, the pace of the Great Acceleration, the increase of temperature of about 1 degree in 50 years, which we are experiencing now, is not unprecedented. So sometimes we listen to people saying the current rate of warming is unprecedented, never occurred before. This is not true. It is unprecedented in the past, maybe 800,000 years, but 800,000 years is nothing with respect to the extension of this 1 million years. It's nothing against the 500 millions. So if you look back into the past history of Earth, there were changes with the same pace, actually. Of course, it's not easy to estimate the pace of past changes because we don't have data. We have just this proxy information. But our perception is that the pace is also not new. Okay. This is a relevant question because, okay, let's also suppose that this is caused by human influence, as it is very likely. It may be that, it is not so concerning for the life of the whole system Earth. It may cause migrations, it may cause adaptation, but if after sometimes it stabilizes, it is something that, of course, it is transformative, but maybe not final. And it's very important to understand that. So the current climate change is leading to human extinction or just to an adaptation of humans. I tell you that the current orientation of the climate scientists, it is debated, but still there are several climate scientists that are convinced that it is probably too early to talk about extinction. We don't see so far in what's going on the risk of extinction. There might be something transformative, which may mean that some lands have to be left and the new lands will become ice-free and therefore usable for agriculture, so people will have to move. And of course, this may originate geopolitical tensions, it may originate wars. You know that now Russia and the United States are looking at the Arctic because if it becomes a commercial route, then there are interests in that. So these are the changes that the current situation may cause, but it is a relevant question to understand if this is compatible with the human life over Earth or not. Keep in mind that we already mentioned that of course our whole Earth system is not going to last forever. What happened to Mars will happen also over the Earth sooner or later, or a meteorite can hit the Earth and sooner or later it may happen what is happening in several other planets. But of course, it's important to understand in a reasonable time scale what's going to happen, because of course death of the Earth system in 10 billion years from now is different than a collapse in 1,000 years. It is unlikely that the collapse will occur in like 50, 100 years or 1,000 years. This is very unlikely. So we are talking of something that is not relevant to us in any case, and it's not relevant to our sons in any case in terms of collapse. It may be relevant to our sons in terms of where they live, yes, but in terms of collapse of the human system, it is not a major risk. And it is important to understand if the major risk may occur in 1 billion years from now, or let's say 10,000 years from now, rather than 10 billion years. This is the level of our target. This is our perspective. So, I mean, in the short term, we are talking about migration, we are talking about geopolitical tensions, we are talking about people that have to move. In the very long term, I mean, we can talk about the fate of the whole Earth system. We can talk about human extinction. This is the general convincement that we today have. But still, I mean, the prediction in the long term is important because of adaptation, because of immediate consequences. So this is the longest picture that we can deal with, 500 million years. Okay? But what it takes to get to this, so what kind of information has been used, okay? So, a global paleotemperature curve is a challenging task. So, elaborating this picture required the analysis of several paleoclimate archives. When I say paleo, it means before the instrumental period. So when I talk of the climate in the Middle Age, 1500, is paleoclimate, okay? Okay, we can use a series of paleoclimate proxies. What does it mean, proxy? It means that we are not talking about a direct measurement. We are talking on another type of information that we link, we connect to a temperature data, okay? Let me look at the chat, sorry, because I want to make sure that I'm not missing anything. The chat is not here. This is a transcription chat. Okay. It seems that there is nothing there. Okay, very good. So, proxy data, okay, is not a direct measurement. It doesn't mean that somebody 500 million of years ago went with a thermometer there and took the measurement of temperature. It means that we measure something different, and then we need to create an association, a link between the something different and the temperature, okay? And possibly we try to look for more than one proxy, several proxies, in order to reduce uncertainty, okay? And then we need to integrate this data into a very rigorous framework, because when we deal with science, scientific analysis, we have to be very rigorous, and we elaborate those that are called dating methods. Okay, okay, perfect. So this is a first example. I already showed to you this picture. It's Monte San Nicola in Sicily. And it's a good example because you see the layers, okay, the stratigraphy. And if you look inside these layers, you find remains, fossils, something that is a very good indicator, because, for instance, if you find there in a layer something that today you find in Iceland, it means that probably that layer, when that layer originated, there was a colder temperature. Okay? The opposite examples can be made. If you find something that lives in a very hot climate, much hotter than the current climate in Sicily, and you find it in another layer, it means that when the layer formed, the temperature was much higher. And therefore, if you look layer by layer, you can reconstruct something like up, down, like today, because maybe in some of the layers you find the same pollens, the same fossils, the same traces or like isotopes, which we will discuss later, the same isotopes as today, and then you can say, okay, the temperature, the living conditions were more or less the same as today. So this is a first thing, but of course it doesn't suffice that you just look at the picture. Okay, it is not just enough to look at the picture. You have to go inside there, and to go inside there, you cannot walk over these layers. You have to, in a way, probe them. Okay, you make a carrot, you go on the top, and you dig. You make a carrot, you go down, and you take a sample over several different layers. It is not easy because, you know, these are not soft layers. They are rocky layers. You see, it is very steep. Steep means that it's very solid. It's not soft. So, or maybe that we can look for other things like limnology. This is a very relevant piece of information. We go to a lake, a very old lake, and then we take a carrot from the bottom of the lake, and then we get information on the fisheries, we get information on the gases that are included into water, etc. Or, as we will see, ice probes. Ice is very easy to probe. Okay. In fact, this is an example of carrots that are taken from the sea bottom. This is marine sediments, is another relevant source of information. I'm giving you examples, okay? Now I'm just discussing examples, stratigraphy and probing marine sediments, limnology, another example that I gave. And for instance, these pictures are taken from the website of the International Ocean Discovery Program. It's IODP. Okay? There is a website and you can take a lot of information. There are several cruises continuously ongoing to take samples from the ocean bottom. And you see a picture of the samples up there. Okay, of course, a picture of the samples here. I think I have a YouTube video somewhere. Yeah, this one. If you don't mind, we can spend 4 minutes to look at this video. Okay. So to look at the video, let me hope that I can do this. Okay, of course it's YouTube, so we will get some advertisement, maybe. Let's see. It's something that I can't believe. I think I made a mistake in the copy and paste. Let me see. Yeah. Okay, now it should work. I tried it just 10 minutes ago and it was fine. So let's see. YouTube watch keyword. One second. Otherwise, no problem. I mean. Okay, no problem. I think, let me just check. Let me make a last attempt, okay, with another browser. Yeah. Okay, for some reason I can't succeed. Anyway, no problem at all. It was not really. Okay, it is not really important. Just in this picture, you can see a map of the sampling sites. The video was basically explaining, and you can make an attempt to see yours by yourself. It was basically explaining the complexity of taking a probe from the bottom of the ocean, because the probe is taken by a ship, and the ship, of course, goes up and down because of the movement of tides and the movement of waves. And it takes a long time to take the probe. But given that it's essential that we know the depth of the carrot, the depth of the carrot has to be monitored by taking into account the up and down of the ship. And therefore, there is a stabilizer inside the ship. It's a very interesting video because it shows how the motion of waves and tides is surveyed and given to the stabilizer that updates the information on the depth of the probe. So it is just an explanation in English of how these samples are taken. I think it is nice, but anyway, I will try in the break if I can succeed. And here you see other information, and they mention also 3 rings. Basically, you see there, we need geological, biologic, like sediments, corals, 3 rings, materials that preserve evidence of past climate, or at least past changes in climate, okay? Is still a very important information. There are several research projects ongoing on that. And the reason is that we recognize the importance of this activity, the importance of reconstructing the past climate. And another very interesting source of information is the exploration of the ice lengths and ice cores. First of all, we spend a lot of effort in monitoring the dynamics of the polar caps, monitoring what's going on, how the ice melts. They are subjected to melting after global warming. And we are interested in how this melting takes place. What is the dynamics, the evolution? We are much interested because knowing the dynamics allows us to make predictions on the pace of this melting. Will it be fast? In the past, it has been a fast melting with maybe some step changes or a very gradual melting. This is an important information. So we monitor these step changes like glacier outbursts of maybe liquid water trapped into the ice, which may suddenly come out and originate floods. And we monitor also the ice layers, because clearly you can recognize layers. As you recognize layers in the rocks, you can recognize layers into the ice. And, you know, these layers, each layer contains information like gases trapped into the ice, other information. Gases means information on the composition of the atmosphere, which is very relevant, like CO2 concentration. Past CO2 concentration has been inferred, has been investigated by looking at ice probes, because there are bubbles of air trapped into the ice, and therefore we can analyze the pace, the progress of CO2 concentration in the past climate. And here is another picture showing the distribution of sites included in the paleoclimate, in one paleoclimate archive. This paleoclimate archive that is mentioned here, the World Data Service for Paleoclimatology by the NOAA of the United States, National Ocean and Atmospheric Administration. This paleoclimatic archive is very important, contains a lot of information, and it is also possible through the website to download the data, part of the data, and also to interrogate the website regarding features that have been observed at a particular location. It is indeed interesting, and as you see, the distribution of the location of paleoclimatic archives is very dense. I mean, it's not very dense because we are talking about the whole surface of Earth, but still there are several information available, and information is continuously increasing. A problem that we face is that the distribution is not homogeneous. It is more dense where in the Western world, it is more dense in the locations where it is relatively easier to go and make monitoring. But for instance, also over the Himalayas, there is a very intensive monitoring campaign for the specificity of the environment. It's very specific and therefore delivers very specific information. Okay, so let's try to look at more details, what we are looking for. So the archives, here you see on the left of this slide, 4 examples, 4 types of archives: marine sediments, which we already discussed, lacustrine sediments, technology, ice cores, we already discussed these very briefly, but we discussed these. Speleothems, what are the speleothems? Are the information that we can derive from caves. You know that caves deliver a lot of information about past water conditions. Caves were originated by erosion triggered by water. Where there is a cave, there was water flowing, and this water is trapped, some of it is trapped into the, I don't know how to pronounce in English, but the concretion, stalagmites, and in the caves. So it's trapped in the rock of the caves. Is trapped some water also into the caves in forms of liquid water. And from the composition of this water, we can derive information on the past climate. So when we talk about speleothems, we talk about paleoclimatic archives coming from caves. Okay, and here you see some of the proxies that can be derived from each archive. Chemical composition, stable isotopes. We didn't talk about stable isotopes. We will talk about them very quickly. And particle size, fossils. Once again, I'm sorry if you can avoid to speak because I can listen quite well what you're saying and this distracts me. So particle size, fossils, spores, and malacofauna, etc. I am particularly interested in discussing with you today stable isotopes because these are indeed a source of information that is very used. Okay, let me move forward sorry. First of all, we can talk when we talk about data derived from paleoclimate archives. We can talk about direct information and indirect information. What is the difference? Direct means that we can make direct measurements of the proxy of interest through, for instance, let me refer to CO2 concentration. CO2 concentration is another climatic variable which is very important. When I take an ice core, then I can look for bubbles into the ice core and measure the CO2 concentration directly into the bubbles. This is a direct measurement. This is not possible for temperature, for instance, because of course we don't have any direct remain of temperature inside any paleoclimatic archive. For temperature, we have to establish a relationship between a proxy, which may be an isotope, we will see what isotopes are, and temperature. But of course, this relationship between like a 3-ring width and temperature has to be established through a model. This relationship is an analytical relationship that is like a model. Okay, so for instance, the model is relating the 3-ring width with temperature. And the model may be based, for instance, on the fact that for the same tree, I see that in modern times, the growth every year of the width of the ring is 1 millimeter. when I see that there is, in the past, an increase of width of the ring of 1 millimeter, my deduction is the temperature was the same as today. Or when I see 0.5 millimeter, my deduction is temperature was 3 degrees lower. This means establishing a kind of analytical relationship between something that we measure directly, which is not my climatic variable, for instance, is treating width, and the climatic variable. There must be a relationship, and this relationship is essentially parametric. Parametric means that the relationship is given by an analytical formula with parameters. Parameters are coefficients that need to be tuned, and therefore tuning is a synonym of calibration. When I say need to be tuned, I could say need to be calibrated. So calibration is required. This tuning, calibration, entails some uncertainty and entails some procedures that we need to set up. So it's important to keep them, to make the difference, to mark the difference between what is directly observed and what is calibrated, okay? So, for instance, here you see bubbles into an ice core. We can measure CO2 concentration directly, okay? And so we can get a picture like this. This is a reconstruction derived from ice cores of CO2 concentration for the past. Here in the picture you see these are years before today, so 400,000 years ago. But actually, we have some reconstructions from ice core that go back up to about 800. And we can conclude that, for instance, you see here, for 650 years in the past, 650,000 years in the past, atmospheric carbon dioxide had never been above this line, which is the 1950 level. So the 1950 level in the past 650,000 years was never exceeded, and now we are at this current level. So you may say this is something that we are told several times, and you may say this is dramatic. Actually, it is 500,000 years. If you go back like 4 or 5 millions of years ago, this concentration in the atmosphere of CO2 was twice than the current concentration. So this is a picture that is somehow still limited. And it is extremely important when you look at a figure like this one, that you look at the time scale. Okay, when we talk about climate, the time scale is extremely important. And you see that for this extension of 650,000 years, the depth of the core is 2.2 miles. It is indeed a very deep core. Okay, so we go deep for about more than 3 kilometers in the ice. Of course, the depth that you can reach depends on the location, depends also on what you are probing. If it is ice, it is relatively easy to go very deep. If it is something rocky, it's, of course, much more difficult. Okay, and this is the website of a project called EPICA, which is precisely aimed at getting ice probes from Antarctica. But anyway, there are several, as I said, several research projects of this type ongoing. This is just an example. Now, this is a slide that is requires a little bit of concentration. So, I talked about indirect measurement, calibration. So, what is an example, a very meaningful example of something that, a proxy that can be used? So, I made the example of the air bubbles for measuring CO2, but if I want to study temperature, what is a meaningful example of something that can be used? And the meaningful example is given by isotopes, stable isotopes. So what is an isotope? An isotope is a particular configuration of an atom. With a particular configuration, I mean the configuration of the nucleus, the number of protons and neutrons, because the same atom, like oxygen, may have a different number of protons and neutrons, different combination. There are some combination of the number of protons and neutrons that are so-called stable. Other combinations that are unstable. What does this mean? It means that when an atom originates, and the number of protons and neutrons are determined, there are some configurations that they are called stable because they are not subjected to natural changes. They can, experience changes if we provoke them, if they are provoked. But if they are not perturbed, the number of protons and neutrons doesn't change. And these are called the stable isotopes. There are some configurations that are unstable. They tend to decay. And when they decay, they produce energy. Okay. So if the configuration is unstable, it changes. So basically, what we observe, for instance, into the ice probe, the isotope that we observe into the ice probe is not the same isotope that was there when it was trapped into the ice. If it is stable, then we can conclude that the number of protons and neutrons is the same today as the age of the layer where it was detected, so as 500 million years ago. And therefore we can say, good, 500 numbers of years ago, there was this isotope there. 500 millions of years ago, there was this isotope. Isotopes may refer to different elements. What is very frequently used is the oxygen isotope, or the deuterium, which is the isotope of the hydrogen. Definitely, we use much more the oxygen isotope, which is embedded in the atmosphere and in water. And here you see the isotope, which is called oxygen 18, and the symbol is sigma 18O. Oxygen 18 means that the atom counts 18 neutrons, and it's stable. But oxygen has another stable isotope. It is oxygen 16 with 2 less neutrons. This means that the atom is a little bit lighter, less weight. Okay? And you may say, yeah, but the difference must be very tiny. Yes, it's very tiny, but it's still a difference. It's the weight is different. So, for instance, if we refer to ocean water, we can define a ratio of oxygen 18 with respect to oxygen 16 in the ocean water. Let's refer first of all to the value of this ratio in the standard mean ocean water. So basically what I do, I take a sample of water from the ocean and I measure the ratio of the number of atoms of oxygen 18 and the number of oxygen 16. Okay, and of course, I get a ratio perfect. Now I can compare the same ratio found into the probe. So in the sample, as AM states for sample, I compute the ratio of oxygen isotope, oxygen 18 divided by oxygen 16, and I make the difference with the current standard, and I divide by the current standard, and then I multiply by 1000 for reasons of dealing with tractable numbers, and then I get an indication of what was the difference in terms of oxygen isotopes in the past with respect to today. Why this is important? You may make this. You may compute the same difference in, for instance, into the air bubbles trapped into the ice cores. Okay. Why is this important? Because given that the isotope has different weight, when it comes to evaporation, when water evaporates from the oceans, the lighter isotope have the priority. They evaporate first. So when I get evaporation into the atmosphere, I first get an evaporation of light water when there is light oxygen, when there is abundance especially. And then there is, with reduced incidence, evaporation of heavier oxygen. Of course, if the heavier oxygen becomes dominant, then it evaporates, has more chance to evaporate anyway, even if it's heavier. So, once again, why this is important? I jump forward a couple of slides. More than a couple. I jump to this figure here. So let's suppose that we are in a greenhouse world, okay? A warm period. So we have preferential evaporation of light oxygen, and then we have preferential condensation of heavy oxygen because it's heavier, so there is also a difference in condensation. So basically, we have now to read these numbers, I want to make sure that I don't make mistakes. So you have more evaporation of O16, and you have precipitation with less O16. But basically, if nothing is trapped into ice, you have everything that goes back to the ocean. Okay. What happens when it becomes icy? The ice is enriched of O16 because it has a evaporation. So O16 remains trapped into the ice, and then the ratio in the ocean and the isotope O18 becomes much diffused. So basically, if you look at the ratio O18, O16 in the ocean water, and therefore, for instance, from the marine probes, and you find the situation where O18 is more abundant, it means that it was a cold period. Conversely, in the ice, you can see the difference. When you see in the ice more O16, it becomes a cold period, and etc. So there is this difference in weight that allows us to distinguish between cold and warm periods. Look here, interglacial period, high temperature, and ice decay. Oceans are not depleted in O16, and low O18 values within, for instance, foraminifera shells fossils. This is something that we can also explore. I will tell you later. Glacial period, low temperature, and ice growth. Oceans are depleted in O16 and high O18 values within foraminiferous shells. So you can distinguish between cold and warm periods. Okay, so when in this case, when data, sorry, earlier I said sigma, this is a delta. I'm sorry for the confusion. When I nominate Greek letters, I always make mistakes. When data is positive, the sample is enriched in area isotope, of course, you see here. When data is negative, the sample is enriched with lighter isotope. Okay, so we look at this ratio, negative, positive. Positive means with respect to today, more area isotope, lower temperature. Delta negative, it means with respect to today, there is more in ocean water, lighter isotope, which is not trapped into the ice. And therefore, it means warmer temperature. In nature, there are about 350 stable isotopes for, if I well remember, 80 elements, 80 different atoms. One is oxygen, the other one is deuterium, but there are many others, there are 80. Oxygen is very convenient for us because it is trapped into water, it is trapped into the air, and if it is trapped into water, it remains trapped into the cells, for instance, of the foraminifera, of the fossils. So basically, by looking at the fluctuations of data from layer to layer, we reconstruct the past temperature. I think I already have an example here. This is a recent contribution, it's about 15 years ago. When I got graduated, a contribution that was like 30 years older was very young, so a scientific contribution, I mean. So in 1992, when I got my degree, we were still using formulas for estimating flood frequency of the 1950s. They were 40 years, age, but still we assume they were very recent. Today, with the progress of science that is very fast, when we see a contribution of 2010, we say, not very recent. It's already 15 years old. Keep in mind that, especially when you talk about Earth system and Earth system sciences, a contribution that is 10 years older, it's already, I mean, you have to wonder whether it's still the latest news. You have to look for maybe more recent contributions. And currently, I see that there are a lot of references in climate science and in water science after 2020. A lot of contribution of 2021, 2022, already 2024. So it is progressing very quickly. Not sure whether this is always a good thing, but yes, in general, it is a good thing. So what you see here comes from a contribution of Valérie Masson-Belmotte, very famous climate scientist. She's still active, and it is dated 2010. So what is this? If you look at temperature change from today, and we go back before present from 0 to 800 kiloyears, in this case, so 800,000 years ago, the construction of temperature. And here you see again temperature, and from 800,000 years ago, from today to again 800,000 years ago, and this is temperature change, and this is temperature change from 1950, from the temperature of 1950. Similar figures, and this one is from another author. Okay, so it is the period is the same period but this is from another author, and maybe that they analyze a different proxy. We are not interested in getting the details of the differences among these pictures. What is important to notice is that there is a lot of variability. It is confirmed, a lot of variability in temperature, okay? So this is a result from isotope concentration, oxygen isotope concentration, okay? A few more words about the foraminifera. The foraminifera are marine organisms and very microscopic. It's sand size dimension, and they are ubiquitous, and therefore they are very convenient because also they are very small size. So given their very small size, they are easily trapped into the sediments and into the probes. What they include in their shells is precisely information about oxygen isotopes. And therefore, when we talk about isotopes, very often we talk about isotopes from foraminifera. So basically, you see the chemical formula of mushroom, and you see the oxygen there. And therefore, they collect atoms of oxygen from marine water. This is why we are interested. And this is another example of a core from the deep sea where we look for foraminifera. And you see that is written here, high sampling frequency. This is a good advantage. And picking of foraminifera to reach the amount necessary to obtain valid values of oxygen isotope. And then, of course, we have to locate the depth of the cores into time. But I mean, this is the subject of, I would say, a research branch that is already a classic, okay? What can we see here? Information of past temperature and derived from marine cores, the green one, and from ice cores, the upper one. Derived this information from delta oxygen isotopes. Why this is important? You see a general agreement in the patterns of these two curves with a shift in temperature, and the scale, the green scale is on the left, the orange scale is on the right. And what is then the difference? Why different temperature? Because the green is taken from marine cores and reflects the temperature of water. Okay. The yellow is taken from air trapped into the ice cores and therefore reflects the temperature of air. And so we can also get a comparison between the temperature of marine water at that time and the corresponding temperature of air. Of course, the pattern is similar and shows once again a lot of variability. This goes back 400,000 years, okay? Okay, this is just a recap. Basically, when we look at the concentration of oxygen isotopes into the shell, we get information about ice volume and information about temperature, which allows us to, in a way, to reconstruct, it's our target to reconstruct the conditions at that time, okay? And this is our take-home message. So, we already mentioned these considerations, these conclusions. It's just a recap, okay? Delta 18 positive means Earth was colder. If it is negative, Earth was warmer, okay? And these records can be taken from the foraminifera shells and can be taken from other remains of the past climate. Good. We already discussed this figure, and let's try to look at other examples, okay? Other examples of proxy data. Another information that is widely used is the distribution of living organisms in the sea, the current distribution, and the distribution that we can retrieve from inspection of fossils. I mean, when we get probes from the marine bed, from the ocean bed, we get, of course, indication not only about the composition of the shells, but also indications from the kind of species. And therefore, for instance, for this species called Persistis thrombus latus, which we know that today is diffused in the East Atlantic. You see the yellow band around Senegal here. But we find fossils into the Mediterranean, and we can date these fossils. So it means that, in a way, the Mediterranean, at the time the fossil was collected, was warmer. Because if the same species that now is a warmer climate is found in the past in the Mediterranean at a precise date, which we can locate, we can say that at that date the Mediterranean was warmer. Similar things for another species called Arctica islandica, that is now, it can be found in Iceland. Okay, today, we find also it in the Mediterranean some time ago, at another date than the Persistis thrombus. So we can say, perfect, in that other layer, which we can date, where we find in the Mediterranean, Arctica, climate was colder than today. So by analyzing the distribution of these fossils, without looking for the isotopes, we can derive information about past climate. I mean, why I am providing these examples? Because we want to understand how the first card that I showed to you from the Smithsonian Museum, going back 500 millions of years in the past, how these cards were reconstructed. And you see what kind of different information that we have to put together. So the Persistis thrombus, I forgot to mention this, to give a precise date. It has been found in the coasts of Italy between 130, 110 kiloyears before present. So this is a period where then the Mediterranean was warmer. Italy was warmer. There is other information that we can look for. And for instance, the record of past vegetation, the pollens or seeds, okay? Pollen grains are microscopic, usually about 15 to 100 microns. And not sure microns is a correct pronunciation, maybe micron, okay? I apologize for that. And seeds is another type of information. So basically, records of past vegetation is an additional proxy data, and we find them in probes, marine sediments, limnology, probes from the bottom of lakes. And then this is something that we can put together. And for instance, if we look at the current distribution of vegetation, and here you see two examples at our latitudes, the Mediterranean forest, at high latitudes, the tundra. So if we find remains, pollens from tundra at our latitudes, and we can date them, At that date, the climate was colder. This is another example, another additional information that we can get. Okay, glacial vegetation, interglacial vegetation. Glacial interglacial, because we are also very interested in trying to learn more about glaciation, interglacial periods, and variability within glaciations, because we will see, I think it's already here. This is a reconstruction that goes back from today up to 60 millions of years ago. So 60 millions is like 1/10 of the Smithsonian reconstruction with which I started today. Still, this was before, this is a reconstruction that was derived also quite recently, but it was already considered a very long reconstruction. With respect to the reconstruction of the Smithsonian, you see that here there are more details. The reconstruction by the Smithsonian Museum was more smoothed. And the reason is that, you know, in this case, they went back in the past for a shorter period. They could use more information, put together more information. More information needs, means more detail. And therefore, they could reconstruct this curve, which shows that even during the last glaciation, and the last glaciation is during the Pleistocene. Okay, look up there. Pleistocene, it's about here. Okay, and you see that here, about 10,000 years ago, a little bit more, temperature went up, and in the Holocene you have quite a stable period. And this is a period which is unusual stability. Unusual stability. Okay, the current period where we are living, unusual stability. So this is the last glaciation. But even during the glaciation, you see variability. So there is a long-term variability superimposed to a short-term variability. There are several climate cycles superimposed each other. By the way, there are some theories postulating that this variability is an essential ingredient for the resilience of the Earth system, for the resilience of living organisms. Because when a system is subjected to continuous shocks, it becomes more resilient. There have been studies recently that prove that when a population is subjected to frequent small earthquakes, they become more resilient with respect to earthquakes. Of course, a disaster is killing a population, but if a population is subjected to frequent moderate shocks, it becomes more resilient with respect to a population that is not shocked at all. And this is valid for earthquakes, is valid for droughts, is valid for floods. I give you an example. There was a huge drought in the United States called the Dust Bowl. I suggest you to look at the Wikipedia page for the Dust Bowl because it's very interesting. It's very, very interesting. And you look at Dust Bowl Wikipedia. Okay. And it is very interesting. So this was a drought that occurred in the prairies of the central United States. And what is the reason? The reason was that these prairies were subjected to a long period with a lot of rainfall. Let's say end of 1800. There was a period lasting about 30, 40 years with a lot of rainfall. So what occurred is that people thought of cultivating these areas, which were not cultivated before because there was no water available for irrigation. And then the people realized that there was a lot of water there and went there, and the US administration found them. They moved there and started agricultural cultivation. And suddenly the climate changed and they got less water. And also they used the tillage technique. So they tilled, they for cultivating crops, they had, of course, to work the soil, and they work the soil in a way with few protections against the wind storms. So a drought period came with a lot of wind, and then this is why Dust Bowl, which forced several people to migrate. What is the meaning of this example? The meaning is to say that if you get a period with very favorable conditions, a lot of rainfall, a lot of water, and a few shocks, then the system becomes less resilient with respect to a system that gets shocked once in a while. So if I go back to our figure of variability of climate, some people postulate that this variability is the reason why we have nature over the earth and we have a resilient system, a resilient earth system. But you see, this reconstruction is extremely interesting because it also shows that conversely, we are living now in a period which looks unprecedented, with some uncertainty, of course, but looks unprecedented, a stable period lasting for already 10,000 years. So the question is, should we expect now the onset of a period with more variability? This is the big question, okay? And then, because it's stable, you see agriculture and civilization. Do you have any question? Okay, let's make a 15 minutes break now. Thank you. Okay. From this subsequent picture, you can see that they marked here the interglacial periods, what are called interglacial periods, which are relatively warm periods within a glaciation. And they were relatively long-lasting, relatively compared to the Holocene, the duration of the Holocene so far. And you see also identified with the acronym LGM, the last glacial maximum, which is, let's call it in this way, the top of the last glaciation, the top low temperature, so the lowest temperature of the last glaciation. And then after the last glacial maximum, you see the increase of temperature and the stability, the relative stability of the Holocene. And also you see here the great acceleration, which is the very short tail before 2005. Here you see a picture of the shoreline during the last glacial maximum, when the level of the sea was about 120 meters below present sea level. And you see that indeed the extension of the ocean was much more limited with respect to the past, but you have to with respect to today. But you have to consider that it was the level of the ocean was 120 meters below the present level. Here you see another important reconstruction, which was derived it was about 20 years ago, was presented about 20 years ago, which was derived by taking the average of 57 globally distributed records of isotope oxygen 18, and you see the location of the sites where samples were taken. And therefore, they obtained with this reconstruction, with these samples, a reconstruction which is presented, I'm sorry, here. One second. Okay. This is extended. If you see the top graph is extended before present on the left, 0, up to 1,800 years ago, kilo years ago, sorry. And then in the graph below, you see the same picture, but starting from the end of the upper picture and going back up to 3,600 kilo years ago. This is another indication, quite detailed, because the level of detail here is, if you look at the time scale, is a very important level of detail. And in the picture, you see the numbers of the samples, which if you go back to the distribution, you see numbers are also available here, I think, yes. And you can see the number of the sample, the location, and the location of the sample that allowed the reconstruction. The level of detail is very fine. What we see is indeed the presence of important climate cycles, many climate cycles, superimposed into a general cooling trend. General cooling trend, because if you look at the period, it is during the glaciation, during the onset of the last glaciation. So we can see the cooling, but we can also see the high variability. And what is the take-home message? The take-home message is that the stability that we are experiencing today is something really unusual. It's something really unusual. It is true that it is a relatively short time scale, the Holocene, but still we can see that the past was characterized by high variability, even during glaciation. So it doesn't really depend on the warm period, cold period. It is an inner variability of climate, which I mean, it's for sure due to a multiple causes. So it's not just one. If it was a volcanic eruption causing a cooling, okay, it is an event. But when you see this kind of variability, of repeated variability, it is for sure due to something that we still don't understand. I'm sorry. Okay. So what is the periodicity? You see that we can identify different periodicity. So there are some cycles that may last for 100,000 years. There are other cycles that may last for less than that, like 40,000 years. So this change of periodicity, it is indeed something that we often observe when we look at past records. And sometimes we observe periodicities with even smaller length, smaller time windows. So it looks like an inherent feature of climate that is subjected to different kinds of variability superimposed each other. Variability at multiple frequencies. This is the correct terminology. And once again, this may be an essential ingredient of resilience of the Earth system. So it could be indeed a inherent feature of the whole Earth system, this superimposition of variability at different frequencies. Now, let's look with more details at the Holocene. The Holocene, we said that it is relatively stable, but it is indeed stable or this granularity that we can observe here. Can it be an indicator of a variability at high frequency? So let's look in better details at what happened as far as we know in the past 10,000 years. Okay, so if we look at more details, we can see, and this is a zoom. If you look at this figure, it is a zoom in the period of years from 8 to 11,000 years ago. So we can say that indeed there are some still inner variabilities inside this stability. Of course, it's a variability on a smaller scale in terms of amplitude with respect to what we observed in the past. It's a variability where we can identify a millennial scale, small amplitude events, less amplitude, I said, and we can identify an important event in terms of change of temperature about 8,000 years ago. But let's look at more examples, okay? So this is, for instance, a map of climate anomalies during the 8,000 years ago events. And this is the upper figure temperature, and the lower figure identifies the effect, the impact in terms of rainfall, because it is also very important that we try to understand, we try to answer the question, what happens to rainfall regime when precipitation regime in general, when there are changes in temperature? This is something, it's an important scientific question. It is something very relevant because, of course, rainfall, precipitation is regulating the water cycle, is determining water-related risks, droughts, floods, is determining also our capability to produce food through agriculture. It's really determining, it's an important ingredient for the human evolution. And rainfall is much more difficult to decipher. We already discussed this because it is highly variable in space and time, and therefore it is this variability, this increased variability makes it more difficult to distinguish between change and, again, variability. And let's look then with more details in the very recent period, last 2,000 years. And this is what we can understand. This is the variability we can understand. It's a reduced variability because we are talking about changes in temperature, which are of the order of magnitude of few degrees or a fraction of 1 degree, like the change that we are experiencing today. And we can identify these warm periods, the Roman warm period, the medieval warm period, and a couple of cool periods. One about the death of the collapse of the Roman Empire. This warm period, this cold period, has been hypothesized as a possible cause of the collapse of the Western Roman Empire. We will discuss this later in a few minutes. The medieval warm period, it is well known. Well known, there are witnesses of people crossing some passes in the Alps that are today covered by glaciers, and people were crossing them without touching any snow, without walking on any snow. And there are several other examples of the medieval warm period, and which examples that are derived from myths, from stories that have been reported from generation to generation about differences in climate. And also we have some marks taken by monks in monasteries where they took notes about agricultural production, they took notes about the pilgrims that were hosted by them. And it's clear from these reports that during the medieval period, there were conditions favoring agriculture, favoring traveling, because one thing that we understood by analyzing these reports is that we can associate warm periods to societal welfare, to expansion of the societal organization, because a warm period means less flooding, because we associate indeed flood frequency to colder periods, basing on the historical marks. And we associate warm period with agricultural production, very powerful agricultural production, and with attitude of people to travel, because first of all, in a good weather, in a warm weather, it's easier to travel. But people also travel more because they have more resources, because of the good agricultural production, which means welfare. Of course, it is not granted for sure that what we experienced in the past will be experienced today, like now, global warming. Can we associate it to an opportunity for some reasons? This is not sure, because the society organization today is much different with respect to the past. And this is something that we have to take into account when we compare present situation, present climate, to past climate. If on the one hand, we can assume that the physical laws are the same, so if we determine that a warm period for some physical laws means less flooding, for sure the same physical laws apply today, but the impact of extreme events, the impact of climate depends on two things: climate, for sure, but also depends on the humans, on us, how we are organized. If we are well organized, then the impact is lower with respect to a situation where we are not organized, we are not resilient. So it is not granted for sure that our organization will react in the same way as in the past. So what in the past was an opportunity can be today a problem, and the opposite also applies. A problem in the past can be an opportunity today. And this is something that you have to consider, that our societal organization, our availability of technology, of other resources like something that we can now use like energy and clean energy, it's unprecedented. This is for sure unprecedented. So climate change may be debatable if it is unprecedented or not, but the impact may be unprecedented because it is unprecedented, the societal organization, our way to react to these events. So what are further demonstrations of the consequences of, for instance, the Little Ice Age? It is the picture that you see on the right, people skating on the Venice Lagoon in 1789. The Little Ice Age lasted up to the end of the 1700s. And also we know that in the Apennines, there were glaciers that now disappeared. And we know that temperature indeed started to increase around 1750. So if global warming with the magnitude that we are experiencing today is something that started from 1990, we have also to be aware that when we talk about sea level rise, the trend started in 1750. And also about temperature, there is a global increasing trend that started with the lower magnitude than today from 1750. By the way, the onset of the Little Ice Age, it is deemed to be one of the reasons of the collapse of the Este family. They were dukes here in our region, in Ferrara, Modena, Parma, and they made a lot of investment during the medieval warm period on agriculture. And then the Little Ice Age came with a lot of flooding, and they collapsed. It is deemed to be one of the reasons why they collapsed, because they invested a lot of money and their economy was not able to, in a way, to react to the flooding. Keep in mind that the way we react to flooding depends on the resources that we have available. And the way we are impacted from flooding also depends on the resources. Because to give you an example, if we don't take care of river maintenance, we are more exposed to flooding. And this is what happened to the Este family. They were more exposed to flooding because they had less resources, and most probably the maintenance effort for rivers, for canals, for irrigation and drainage were lower, and therefore they got more exposed. Indeed, changing climate superimposed to lack of resources may be the reason for the collapse of some societal organizations. So the default of a nation may occur also for climate change superimposed to lack of resources. So public debt, for instance, is a bad indicator, is an indicator of not good health against natural disasters, against natural hazards. Okay, anyway, around 1500, people in Venice, they had fun skating on the Venice Lagoon. This never occurred after that, okay? So, what is our conclusion so far? Earth's climate system is extremely variable, clear, okay? If we want to make a recap now, after almost 3 hours of lecturing, this is the take-home message. There is a lot of variability. But what are the causes? Because if we want to attribute current climate change to humans rather than natural variability, we should have an idea of the causes of human-induced global warming, and we have the idea. It's the increase of greenhouse effect, etc. And we should have an idea of the causes of past changes. So what are the causes? Of course, several theories have been made, elaborated about the causes of climate variability. Let's have a look to some of them. So, for instance, people assumed that it could be, the changes in plate tectonics may have had an influence, clearly, because the climate is also dictated by ocean circulation. ocean circulation determines the transfer of energy in terms of heat from different sectors, different parts of the Earth system. And therefore, if there is a change in ocean circulation, it's a change in climate. You may have heard that now we are observing that the Gulf Stream is slowing down. It's not clear the reason, but it is indeed slowing down. And there are several possible explanations for that, including global warming. If the Gulf Stream slows down, of course, the effect of the Gulf Stream, which is mitigating the winter climate in the north, is going to slow down as well. So we may get colder winters after global warming if the Gulf Stream slows down. This is why sometimes we hear people saying the very cold storm has been an effect of global warming. Because indeed, if it is true that global warming is causing a slowdown, slower pace of the Gulf Stream, indeed, global warming can be the reason for cold winters in the north. And of course, the ocean circulation is influenced by plate tectonics, the position of continents. Another explanation, and I jump down to the yellow rectangle, changes in sun strength. So sometimes we heard people saying, scientists saying, changes in sun's strength is not an explanation of current global warming. This is not certainly true. I mean, we still know a little of sun dynamics, and maybe it's even not predictable. And it is not easy to measure it. So, of course, global warming, I mean, the sun has the power of heating our solar system. So you understand that with a so strong power, even a small change in sun activity can determine a change of temperature of Earth of 1 degree. There is the question is still why. And then there is another possible explanation of changes in the Earth orbit. Because it is proved that, for instance, for the collapse of asteroids, if a planet changes the feature of its orbit, this has a strong effect on the exposure of the planet to the sun energy, and therefore on the distribution of the sun radiation over the Earth. And even a small change in the Earth orbit, which may be caused also by different reasons, not only the impact of an asteroid, maybe also change in the internal circulation of the nucleus, maybe many other things. And then it may happen that there are climate variations. And also you see that the climate is a result of the interaction, we know that, very complicated interaction between the atmosphere, ice, ocean, and surface vegetation. If there is a perturbation of one of these arrows, bidirectional, by the way, you understand that if you break one of them, for instance, or if you limit the power of one of them, then you get a global perturbation. And it's not easy to come to an attribution. The moral of this story is not that we don't know anything. The moral of the story is that we have some missing pieces, and which determine uncertainty. And at least we have to become aware of this uncertainty. Because uncertainty is not a problem when you know it. It's like a problem. A problem is not a problem when you know it. A problem is a problem when you don't know it. Uncertainty is a problem when you don't know it. So, I mean, it's not a problem that we don't understand something. We will never be able to reach a full predictability of what's going on. But if we have an idea of uncertainty, we are all set. Okay, so the moral of the story, the purpose of this discussion that we are having is that we have to recognize uncertainty and make any possible effort to assess it, okay? So changes in the Earth orbit. So there was a brilliant scientist, Milutin Milankovic, who lived between 1800 and 1900, who made important discoveries. And he was Serbian, and he developed full theory in 1941, and at the age of 60. And this is brilliant because you know that we think that the power of the brain for elaborating new mathematical theory starts to go down after the age of 25, 30. This is basically what the statistics say. And important theorems were discovered by mathematicians that were younger than 30 or less younger than 35. Milankovitch is an exception. He finalized this theory at the age of 60, more than 60 actually. And he proposed that natural changes are recurrent over a long period of time due to changes in the Earth-Sun geometry. And he identified some cycles. If you look on Wikipedia, Milankovitch cycles, he identified indeed some periodicity. And notably, there are some periodicity that he indeed explained with changes in these three parameters of the orbits of the Earth and the Sun with respect to the Sun: eccentricity, obliquity, and precession. So, what are these? So, eccentricity can be calculated by looking at the orbit of the Earth around the Sun. And the position of the aphelion is the position of the farthest point in the orbit of Earth with respect to the Sun, while the perihelion is the closest. And if you indicate with A the distance of the aphelion from the Sun and P the distance of the perihelion from the Sun, you can compute the eccentricity with the formula that you see on the screen. No need to remember it, okay? Just remember what is eccentricity, which means that the orbit of the Earth is not centered around the Sun, it's just shifted a little bit. It's a bit eccentric, okay? And then there is the obliquity, it's the inclination of the Earth axis. And then there is the precession. The precession is the inclination of the Earth's axis with respect to the overall axis of rotation of the Earth. Okay, and we can also have a look at this video, but I think it is a bit long. It is 11 minutes. I tried it before the lecture. It is very interesting. It's a video on the Milankovitch cycles, but it is 11 minutes long. So I invite you, if you're interested in looking at it, it is interesting and also a lot of fun. I mean, not boring. A video on the activity of Milankovitch, which analyzed the periodicity that may come from these three characteristics: eccentricity, obliquity, and precession. And in any case, what we understood is that even a small change in any of these parameters, which may occur periodically or for a given perturbation, may give rise to significant changes in climate. And they may be the explanation of these cycles, superimposed cycles of variability. Other explanations are related to the magnetic field of Earth, which is never stable. It has continuously changing magnitude and direction. And we observed in the past some shifts. I think we already discussed this. Shifts means inversion of the poles, which is something that once in a while occurs. And this is due to the internal circulation in the nucleus of the Earth, which may be subjected to some periodicity, because you know this. We know that these fluid flows, indeed, when they are subjected to inertia, and this inertia, like the movement in a pendulum, like a pendulum has a characteristic frequency, also there can be some periodicity in the movement of these fluids, metal fluids in the nucleus of Earth, which may go like not at constant pace, but they may, in a way, subjected to some inertia and periodicity, an inertia that can be derived by some energy they took billions of years ago. And this is another possible explanation of periodicity. Okay. So basically, the conclusion of this is the Holocene was a period of stability. It's a period that is already quite long, but still there is an inherent variability, which we explored and may cause something similar to the global warming we are experiencing today. And then there is the great acceleration. We already discussed it, and it would be very naive to say that it has nothing to do with current global warming. It is clearly the coincidence of the timing and in a way, the pattern of it, so the dramatic increasing pattern after 1950, after the Second World War, which is in a way with some delay, concomitant, concurrent with global warming. So, I mean, this great acceleration and consequent increase of concentration of greenhouse gases has for sure something to do with the current warming, to some extent at least. And maybe that there is superimposition of drivers. Remember that usually when disaster occurs, there are always more than one driver, usually. It's not just one, okay? It is the composition of several circumstances which result into a very unlucky situation. So, I mean, the great acceleration can be an explanation for global warming, at least in part. And this is what is the conclusion also of the National Geographic when defines what is global warming. It can be attributed, at least in part, to human activities, at least in part, okay? And then there are our predictions, which we already discussed. Also, Veronica Rossi wanted to discuss them here. And these predictions, which are derived with climate models, which again, we already discussed, and are in agreement in saying that global warming will continue, and with different magnitude depending on the model that we used and depending on the scenario emissions that we adopt. But we already discussed the great acceleration, and we already discussed extensively the possibility that global warming can be attributed to humans. Here there is a slide on the reaction of coastal and alluvial systems. You may have read on the Corriere della Sera, it was last week, I think it was Friday, an interview to Professor Andrea Rinaldo, former professor at the University of Padua. He was awarded the Stockholm Water Prize, which is like the Nobel Prize for Water 2 years ago. And what he said is the Venice Lagoon is going to die in terms of ecologic life in 60 years, because the sea level rise will cause the closure of the Mose. The Mose is the moving dam that has been displaced in the Venice Lagoon to mitigate the effect of high tide. And he said, okay, in 60 years, so the Mose will be closed for 288 days per year, which means no circulation of water into the lagoon. It means death of the life of the Venice Lagoon, which implies a deterioration of quality, etc., etc. Indeed, there is the feeling that the sea level increase may induce an impact also over the coasts, which it is something that is really realistic also in terms of salt water intrusion. Okay, now what is the moral of the whole story? Okay, this is a conclusion by Winston Churchill. And it means look back for predicting the future. The moral of the story is that we have today means for making predictions. We have means for trying to understand what are the drivers of the current global warming. But still, there is a lot of things that we don't know. And therefore, it is extremely important that we look at the past to understand what is the magnitude of this uncertainty in order to be able to set priorities, because priorities are different if we have to fight against only one cause, CO2 concentration in the atmosphere, or a possible combination of causes. And then it is extremely important that we identify the correct priorities. Of course, from this discussion, you are still not able to identify a priority, to identify a number, but actually, people who are working at the analysis of past climate change are now becoming close to making a prediction. So if it is true, I give you an example, that during global warming, daily precipitation over certain areas has increased extreme precipitation. I'm talking of precipitation that you see very exceptionally, has increased in intensity about 10% in the past 30 years. So if I am able to say that daily precipitation in Bologna, extreme, exceptional daily precipitation in Bologna has increased during global warming during the past 30 years, 10%, I am able to say, okay, if in the future I have another increase of temperature in Bologna of 1 degree, like the one that we experienced in the past 35 years, then I may expect a 10% more of increase in precipitation. This is extremely useful. This is extremely useful because we have to solve this gap that we don't know how to make engineering design in the presence of climate change. If we could have this number, what is the percentage of increase that I can expect from now to 2050 in extreme precipitation, like extreme drought, like extreme heat waves, then I can adapt. But I really need to become able to make such prediction in order to make an adaptation. If it is uncertain, it's no problem. Instead of plus 10%, I will get an indication plus 5, 15%, which is anyway what we need. It's, as I said, it's not a problem uncertainty, it's a problem if it is plus 10% with an uncertainty which I don't know. This is a problem. But if it is an increase of plus 5, plus 15 in this range, that's fine. Okay, and this information that we are collecting now is targeting this purpose. Questions? Let me look at the chat while I shut down. No questions. Okay, see you next Monday. Thank you very much.